This video provides a brief introduction to the analysis of sedimentary provenance, which links sediment to its source area using things like mineral composition, chemistry, or the age of the component minerals. This figure here, just as an illustration, shows one such study. It uses the age distribution of sediments around Antarctica to try and reconstruct the source areas. The color-coded pies refer to specific ages coming from the hornblende minerals. So, I'll illustrate a few principles of weathering and some terms to describe sediment composition and texture, and then provide a few examples of how provenance can be reconstructed. This isn't going to be an exhaustive list, just more of a taste of some of the methods. You'll get some more practice actually applying these techniques in class. So provenance is a term describing the techniques used to reconstruct the source area and sometimes also the sediment transport history of a sedimentary rock from its source to the site of deposition. Typically, these studies relate the lithological or chemical or isotopic or age characteristics of a sediment sample to a spectrum of possible source areas. The picture on the left shows a sandstone composed entirely of quartz with well-sorted grains that are fairly rounded. The picture on the right shows a poorly sorted and quite angular sandstone with a wide range of minerals, including rock fragments. So these two rocks have very different transport histories and likely source areas as well. Sediment is originally produced by the breakdown of rocks in a process called weathering. Weathering can occur from mechanical processes, such as wind abrasion, water abrasion, or freeze-thaw, the wedging of cracks by freezing and thawing of water. That's probably what's happening in the top photo mostly there. Mechanical weathering will break the rock into smaller fragments, and it may increase the roundness of those fragments, but it doesn't really change the mineralogical composition of the sediment that comes from that rock. Weathering can also occur due to chemical processes, the breakdown of minerals due primarily to acidic water, and this does alter the mineralogical composition. So the relative importance of mechanical and chemical weathering differs largely as a function of temperature and rainfall, with chemical weathering dominating in warm and wet regions. Mechanical weathering, in contrast, dominates in cold regions and temperate regions as well. In very dry regions, very little weathering occurs. So this relationship between climate and chemical weathering intensity, at least, does have some important implications for studies of provenance. So if our goal is to relate the sediment to its source region, modifications to that sediment during transport can really make this difficult. And sediments will be more heavily modified by chemical weathering for a given distance of transport in these hot and humid regions. For example, the mineral composition in a river will change quite rapidly downstream in a hot and humid climate. The bottom diagram, sort of cartoon, kind of illustrates how you go from a sediment that contains lots of different rocks and mineral fragments to one that just contains quartz. In a temperate or a cold or a dry or arid climate, those minerals will not break down as quickly, and so over similar transport distances, the mineralogical composition will not change nearly as much. So how do these minerals break down? Well, minerals tend to break down following this Bowen's reaction series, which you might remember from previous classes. What it is doesn't matter that much, but basically minerals that tend to crystallize at higher temperature, like olivine, pyroxene, amphiboles, are most easily broken down during chemical weathering, whereas feldspars and micas, and especially quartz, are the most resistant to chemical weathering. So if chemical weathering is extreme, then quartz may be the only mineral remaining. So all these other minerals, well, what happens to them? Well, all these other minerals ultimately break down and form different types of clay minerals. Calcium carbonate or calcite is sort of an exception. It actually just dissolves completely to give you calcium and carbonate ions. So this breakdown of minerals into clays gives us one important description of the weathering extent. And this is compositional maturity. It's just the degree to which the sediment contains only resistant minerals, especially quartz, but there can also be, in small amounts, fairly resistant heavy minerals like magnetite or zircon or whatever. So an immature sediment, a compositionally immature sediment, will still contain minerals like amphibole or biotite, hornblende, or rock fragments composed of those minerals. Compositionally mature sediments basically only contain quartz, maybe some of these heavy minerals as well. So compositional maturity is a measure of the degree of transport. It is affected by the amount of transport, but also it's important to know that it does depend heavily on the local climate as well. The extent of weathering can also be described by the textural maturity, which is based on the shape and size and sorting of grains within the rock. So it's based on the amount of clay, the sorting of the non-clay or the sand-sized grains, and the rounding of those grains. Texturally immature sediments contain abundant clay, and the sand grains are poorly sorted. There's big ones and small ones and medium ones, and they're really angular, or they have a range of rounding. Some might be rounder, some might be more angular. Clay is the first thing to be removed as the rock becomes more texturally mature. Then finally the sorting increases, and the last thing to really happen is that the grains become well-rounded. So a texturally mature sediment contains basically no clay. It would be an arenite, not a wacky. It has well-sorted and fairly well-rounded, or at least sub-rounded grains. The textural maturity is a good measure of the transport distance, or it's really a measure of the amount of energy that's been used to modify those grains, which is, in a general sense, proportional to the amount of transport. So to finish this video, I'll walk through a few examples of some techniques that are used in provenance analysis. The details of how each method works aren't important. You'll get a chance to practice a few of these in class as well. A real standby method are ternary diagrams. You've probably seen ternary diagrams in previous classes. Geologists love ternary diagrams. In this case, they will plot a variety of things. Really, the most common one is this QFL diagram, plotting the composition, typically of the sandstone, plots the amount of quartz, the amount of feldspar, and the amount of lithic or rock fragments. This can be used to distinguish sediments from different tectonic settings. One of the real key things in provenance analysis is the tectonic setting and the tectonic setting of the source of the sediments. So sediment that contains a lot of quartz typically comes from sort of craton interiors, the interior of a continent. But sediments that contain a lot of rock fragments may be derived from volcanic arcs, volcanic belts, or island arcs. One thing to note here is that the sediment tends to contain a lot of chert, or rock fragments made of quartzite. Those you may modify the QFL to remove those and include those in the lithic category, and just include single crystal or monocrystalline quartz in the Q or the QM corner. This lithic category contains a wide variety of rock types. It could be some volcanic rocks, igneous rocks, metamorphic rocks, sedimentary rocks. And so other ternary diagrams have been developed to plot different categories of lithics. You can plot metamorphic versus volcanic versus sedimentary. You can plot all sorts of quartzes versus volcanic versus sedimentary. And again, workers have used modern sediments where the tectonic settings are known to kind of calibrate these diagrams. So you can see what you would expect the sediment from a magmatic arc in a four-arc basin to look like. Chemical methods are also widely used to reconstruct provenance. The samarium neodymium system is used especially on fine-grained sediments like mudstones to determine whether the source area is dominated by older continental crust or younger, juvenile magmas or ocean crust. In this case, the ratio of isotopes of samarium to isotopes of neodymium are measured with this epsilon neodymium term. I'm not really going to explain what that is because it's not important for our purposes. But basically, the mantle evolves along this green line, the depleted mantle green line. So magma that is removed from the mantle has that composition when it first is removed and becomes a volcanic or plutonic rock. But after the magma is separated from the mantle and crystallizes, the rock composition will then change to become more negative. It'll have more negative epsilon neodymium. So for example, a rock that crystallized 2 billion years ago would start at the green line at a value of 4 or so, but then would evolve diagonally down to the left in this bluish-purple field. So we can use the sedimentary composition to kind of get an idea of when that material was removed from the mantle, and then tie it back to areas on the continent that we know the epsilon neodymium values of. Strontium isotopes, the ratio of strontium-87 to strontium-86, can also be used to distinguish between sort of continental and mantle or juvenile sources. In this case, the element rubidium really strongly goes into continental magmas, and then the rubidium-87 decays into strontium-87. Strontium-86 is found in all sorts of rocks, and so therefore continental rocks, because they contain the rubidium to begin with, have a greater or an enriched strontium-87 to 86 ratio. So in Western North America here, there's this somewhat famous line called the 706 line, which distinguishes rocks. It kind of traces the edge of the old continent, the old craton. It separates the continental rocks with high 87-86 strontium, greater than 0.706 on the east side, from younger or juvenile rocks with lower 87-86 on the west side. So finally, the age distribution of crystals, like zircon crystals that are contained within a sediment, can also act as precise fingerprints of the source area contributions. These zircon grains are called detrital because they're present as detritus in the sediment, rather than primary igneous zircon grains that are erupted from volcanoes. The mineral zircon contains very small amounts of uranium, and so therefore they're very resistant minerals, so they're a real primary target for uranium-led radiometric dating. So I just show 3 samples here, all from Cambrian sandstones. Each of the diagrams shows the age spectrum of zircon grains within those rocks. So in the lower right, there's a sample that comes from Georgia, a Cambrian sandstone from Georgia. You can see that there's a large peak between, say, 1 billion and 1.3 billion years old, or 1,000 million and 1,300 million years old. The nearby Grenville orogeny, along sort of the east coast, inside of the Appalachians there, contains many rocks of that age. This is kind of what you'd expect. The sample is dominated by sediments deposited from a nearby mountain belt, the Grenville mountain belt. In the bottom left is a sample from the Grand Canyon. This has a very different age spectrum. Those 1 billion year old rocks or zircons are very, very rare, but there's a peak at, say, 1.4 to 1.5 and a peak around 1.7. And again, that's consistent, again, with local derivation from, in this case, the Yavapai Mazatzal, those sort of green and brown-colored mountain belts near the green dot. Finally, in the upper left, there's a sandstone from British Columbia, also Cambrian aged. It has a big peak between, say, 1.8 and 2 billion years ago, consistent with derivations from local rocks. But interestingly, there's a small peak around 1 billion years old, even though the nearest rocks of that age are this Grenville on the opposite side of the continent. So those grains, and actually those types of grains pop up in lots and lots of samples across North America, have led to hypotheses about transcontinental river systems draining these Grenville mountains. So these examples aren't intended to give you a complete description of all provenance analysis techniques, but you hopefully have an idea of the breadth of possibilities and the types of questions that could be answered by reconstructing provenance.